In 1852, clockmaker Edward Dent set out to construct the largest and most accurate public clock in the world. It took 7 years to build, a testament to a very human need.
Our modern-day lives are completely driven by precise measurement. Take Big Ben. For over 150 years, it's been ringing out the correct time to the people of London.
When built, it was an engineering marvel, accurate to an incredible 1 second an hour. But times have changed. Today, we can build clocks which lose 1 second in 138 million years. And now there are plans for a clock accurate to within 1 second over the lifetime of the universe. What is it that drives us to such extremes of ever greater precision? Why do we feel the need to quantify and measure, to impose order on the world around us? Since our ancestors first began to count the passing of the seasons, successive civilizations have used measurement to help master the world around them. It's taken us to the moon and split the atom, and it fascinates me.
Ever since I was young, I've been obsessed with measuring things, trying to make sense of the world around me. Where do those measurements come from? I mean, who decided that a kilo was a kilo and a second?
What we measure, how we measure it, and how accurately we can measure it are surprisingly complex questions. Questions which have obsessed generations of great minds and created a system that describes everything in our world with just 7 fundamental units of measurement. And the quest to define those 7 units with ever greater precision has changed our world. In this series, I want to explore why we measure. What drives us to try and reduce the chaos and complexity of the world to just a handful of elementary units? In this first programme, I'm going to be looking at 2 of the most fundamental measurements, namely the metre and the second. It's likely that time and distance were the first things people ever tried to measure. They seem closely linked in our minds. We even talk about length of time. And as we'll see, time and distance are inextricably connected by modern science. Being able to measure time actually means spotting patterns, and that's actually a very mathematical way of looking at the world. In fact, measuring time is an incredibly sophisticated act. So where did it all begin? Our ancestors would have first picked up on the patterns of the seasons, marking time as the leaves turned brown, or the days got shorter, when rivers flooded, or berries ripened. These very practical observations would have helped them in the daily struggle to survive. One of the first examples of humans' attempts to measure was discovered here in southern France by 4 teenagers and their dog called Robot. It was 1940, and the 18-year-old Marcel Ravida was exploring these woods when he came across a hole where a tree had been uprooted by a storm. He needed some tools to make the hole bigger, so he came back 4 days later with his 3 friends, and they uncovered the entrance to a huge system of unexplored caves. But what they discovered inside was even more exciting. Wow. The boys must have been absolutely staggered to come in here and see these images painted on the wall. I mean, these are some of the oldest cave paintings. Oh, look at this. It's all over the wall. Marcel and his friends had discovered some of the earliest cave paintings ever found. These date back 17,000 years and were painted by Cro-Magnon man. It's beautiful.
You can really feel the energy of these animals kind of rushing across the walls.
This cave is a replica of the original, which is a few hundred meters from here and is now carefully preserved. Dr. Michael Rappengluck believes these paintings are evidence of man's first attempt to measure time.
This one, it's very, very beautiful.
I can see the little things.
Yes.
To him, this is a giant calendar. The clues lie in these strange patterns of dots.
Each dot represents a week. 13 dots represent 1/4 of a year.
His theory is that each 7-day phase of the moon, what today we'd call a week, is marked with a dot on the wall to chart the passing of time. It was a distinctively shaped cluster of dots that eventually allowed him to unlock the full meaning of the paintings.
Look up to the ceiling. You see 6 dots. It reminds a little dipper. And I think this is the star pattern of the Pleiades.
Oh, right, so these dots are not representing weeks anymore. These are stars up there.
Yes, these are stars, and they serve to start the year.
When our ancestors saw the stars form this same alignment in the sky, it would mark the start of their year. Dr. Rappengluck believes the animals have meaning too.
The stag represents autumn equinox, and it's starting a time cycle to the horse. The horse represents springtime, and you see the horse is pregnant, highly pregnant. So 3/4 of a year are represented on the wall.
So it's the star calendar, followed by the calendar marking the weeks, that allows them to know when the stags are rutting,
Yes,
or
indeed.
the pregnant
They
animals.
synchronized biological rhythms of the animals with astronomical rhythms.
It's an extraordinarily sophisticated system
Yes.
for 17,000 years
It is.
ago.
It
It's
is.
amazing.
With the aid of this basic calendar, for the first time, our ancestors could start to predict what would happen and when. They could prepare to hunt when animals migrated close by, or as agriculture developed, determine the best time to plant crops. Measurement was making life easier. But as communities grew, so did the need for more precise timekeeping, beyond the cycles of the moon, the stars, and the seasons.
13,000 years after our ancestors painted the caves in Lascaux, first the Mesopotamians and then the Egyptians started to tackle the problem of dividing up the day. And they took their inspiration from the sun.
By observing how the length of a shadow changed through the day, they found an easy way to measure time. And they used a device just like this.
This is a replica of an ancient Egyptian sundial, and it's one of the first instruments ever created to measure time. Now, at midday, this stone here would have cast no shadow, but as the day went on, the shadow would get longer and longer. So the ancient Egyptians decided to divide the day up into 12 units. And you can see the lines here. We've got 1, 2, 3, 4, 5, 6 lines for the afternoon and 6 for the morning. It's just coming up to 3 o'clock.
By linking time and distance, they could reliably measure shorter periods of time, telling the time by measuring the length of a shadow.
Although the sundial was a brilliant invention, it was fundamentally flawed.
It didn't work at night. Like the cavemen of Lascaux, who used stars to mark the seasons, the Egyptians went one step further. They used them to divide up the hours of darkness. But on a cloudy night, just as on a cloudy day, they still had no way of telling the time. And this is where they made a conceptual leap. This is a water clock.
It's a very simple idea. Basically, what they did was to take a bucket and make a hole in the bottom. Then, as night fell, they would fill the bucket with water. Now, as the water drips out, they can use lines marked on the side of the bucket to tell how much time has passed through the night.
They could measure 12 hours independently of the sun or the stars. But why count 12 hours at all? The answer lies in how business was done thousands of years ago. Throughout the Middle East, the number 12 and the number 60 were important in commerce. They're numbers that were familiar to traders in markets just like this. And the reason they used them is all to do with arithmetic.
Well, as a mathematician, I love the answer because it's about the mathematical properties of these two numbers. They're highly divisible. Take the number 60. I can divide 60 beans into 6 groups of 10 beans, 5 groups of 12 beans, 4 groups of 15 beans, 3 groups of 20 beans, 5 there, 2 groups of 30 beans, or 1 group of 60 beans. But take 100 beans, how can I divide that? I can divide it into 2 groups of 50, but divide by 3, I've got to start cutting a bean.
Because the numbers 12 and 60 were so familiar to Egyptians, it was perhaps no great conceptual leap for them to come up with a 12-hour night and day. So the idea stuck. It wasn't just the measurement of time that the Egyptians needed to tackle. They also needed to find better ways to measure distance. Every year, the Nile would flood, bringing great fertility to the land. But with each flood, the borders of the farmers' land would be washed away. So when the waters receded, an accurate way of measuring field size and re-establishing boundaries was critical. They needed a reliable and uniform measure of length. And their solution was this.
It's a cubit rod, and it's the Egyptian equivalent of a ruler. Its length was the distance of the pharaoh's cubit, which was the length from his elbow to the tip of his middle finger. So actually my cubit is slightly shorter than the pharaoh's. But this led to the Egyptians creating some of the most remarkable buildings the world has ever seen.
This is the Great Pyramid of Cheops, built over 4,500 years ago for the 4th dynasty pharaoh Khufu. It's said 20,000 men took 20 years to build it, using over 2 million limestone blocks, all meticulously aligned and measured with the cubit rod.
This is a miraculous building. The length of the side is 440 cubit exactly.
Exactly?
Exactly.
Wow.
And the height is 280 cubits exactly. Also, it's very square. It has perfection in every part of it.
Absolutely, and with so many people working on it, spread over, I guess, a large area in a large amount of time,
Yes.
I mean, actually having a standard unit of measurement must have been absolutely essential.
Exactly. They had a rope which is 100 times this. that has knots in it every 1 cubit or every 10 cubits, which is called khet.
Okay, we want to measure 440, so we need to take the cornerstone as our starting.
Exactly.
And so if you start measuring.
Yes.
The original cornerstones are no longer visible, but the foundations are still here for all to see.
I think I chose the easy job. $430? Wow. 440 cubits,
You
pretty
see?
much on the knot.
Exactly.
What's so remarkable about the Egyptian system is that they were one of the first to standardise length measurement. It's said that every full moon, the surveyors across the land would gather and compare their wooden cubit rod against the royal master cubit. Made of granite, this was held by the royal surveyor. Failure to maintain an accurate cubit was punishable by death. It was a very simple and efficient way to standardise length measurement across the land, and it enabled the Egyptians to measure things with phenomenal accuracy. Mastering and standardising time and length measurement was really key to the success of the ancient Egyptian empire. The power of measurement is that it created order out of chaos and allowed civilization to flourish. The standardization of measurement, which began here in Egypt several millennia ago, is now central to all our lives. Nearly every country in the world has a national measurement body whose master lengths and weights are calibrated by one international body. A little bit like the modern-day pharaohs trying to bring standardization of measurement across the globe. But despite the obvious logic of having one international system, it hasn't been completely embraced. Take me, for example. I'm going to the airport in this cab, which measures its speed in kilometers per hour and miles per hour. When I'm up in the air, they'll be measuring their altitude in feet. My clothes are measured in inches, and my shoes are measured in, well, frankly, I've never quite understood what the unit of measurement for shoe size is.
Shoe sizes aside, standardization of measurement underpins all modern science, though the road to standardization has not been an easy one.
Throughout history, rulers had a nasty habit of ripping up measurement systems and demanding that they be replaced by lengths based on their own body parts. In 12th century England, the yard was defined as the length from the tip of the king's nose to the top of his outstretched thumb. But as each new reign came in, so things changed. Henry VII, he defined a yard as the length of his arm. Elizabeth I, well, not to be outdone by her male predecessors, added a few more inches. And so the chaos continued.
Lack of standardization was a problem on the continent too.
If you thought the British had it bad, then spare a thought for the French. On the eve of the French Revolution, the Ancien Regime had over 250,000 different weights and measures, including several thousand for length. By the end of the 18th century, people realised that something needed to be done. Trade was impossible and open to fraud, navigation was treacherous, and building plans made by an architect in one city couldn't be reproduced in the other because they didn't have the same measurements. The mess was finally sorted out by the French Academy of Sciences. It was the last few days of the French monarchy, and buoyed by the revolutionary spirit of the time, sense of equality and rationalism, France's best scientists decided to form a groundbreaking revolutionary plan of their own. No longer would measurement be based on the human body or the vanity of kings and queens. They decided that it should be based on something permanent and unchanging. They chose the Earth.
It's really exciting to be here. This is really one of the great scientific centres in the whole of the world. And this is where the modern story of measurement really began, where a new standardised unit of length was introduced, one that is familiar to us all today. On the 26th of March 1791, the Academy here decided to call this new length measurement the metre. Named after the Greek word metron, meaning measure, they decided that it should be 1/10,000,000th of the distance between the North Pole and the equator. It was very clever. The Academy knew that a French colloquial measure would never be accepted by the rest of the world. By basing the metre on the planet itself, no one country could argue for their own measure. They had transcended the politics of nations. This is a system for all people for all time, announced the revolutionary government. There was one problem though. Nobody knew accurately what the distance between the North Pole and the equator actually was. Getting an accurate figure would mean embarking on the most ambitious and complex large-scale measurement project ever attempted. Two scientists were tasked with turning the theory into reality. They were Pierre Méchain and Jean-Baptiste Delambre. Their task was to measure the distance between 2 points on a meridian or line of longitude. Then, using fairly simple mathematics and knowing the latitude of each point, they could extrapolate and calculate the distance from the pole to the equator. This experiment would be difficult enough under normal conditions, but France was in the middle of a revolution. It was a dangerous time to have big ideas that were not necessarily easy for the new order to understand. Nevertheless, undaunted, the scientists pushed ahead. It was here in 1793, from this bell tower in Dunkirk, that Jean-Baptiste Delambre started the northernmost part of his epic quest to measure the Earth. While 800 miles to the south, Barcelona was chosen for Pierre Méchain. Their plan was to work towards each other and meet in Rodez in southern France.
You can imagine Delambre's excitement as he stood up here 200 years ago, ready to start his journey. A journey that would take him 7 years to complete.
And the rather splendid piece of equipment they used was this: a repeating circle. A device that measures angles extremely accurately and as good today as the day it was made.
Now obviously Delambre wouldn't measure every distance from here to Barcelona, but what he can do is use a method called triangulation. So the first point of the triangle is the top of this belfry. Then Delambre would have looked across the countryside trying to find two high points, And he would use this piece of equipment to line up the telescopes on those two other points.
Then all he had to do was measure the angle between the 2 points and measure the distance to the closest one. By then moving to the next high point and measuring the angles again, simple geometry gave him the distances between all three.
So it's an amazing principle, because just one measurement of distance and then there's triangles all the way to Barcelona.
Delambre had a number of close scrapes along the way. He was arrested several times, accused of being a spy. Why else would he be scaling towers, carrying strange equipment? He tried to explain that he was measuring the size of the Earth for the Academy of Sciences. But a drunk militiaman interrupted. There is no more academy. We're all equal now. You'll come with us. But in general, they were literally above it all. On rooftops, towers and church spires, they carried out their quest. It was an extraordinary feat. 7 long years later, the two men had measured the exact distance between Dunkirk and Barcelona. Now the meter was just a simple calculation. The result of all Mechin and Delambre's hard labour, the prototype meter bar, is held here at the French National Archives in Paris.
Made in 1799 of pure platinum, it's meant to represent 1/10,000,000th of the distance between the North Pole and the equator. In fact, due to errors that Mechin made early on in his survey, it's fractionally wrong.
The errors that Mechin made were pretty much irrelevant, because for the first time, the world had a unit of length that was based on something they believed was permanent and unchanging: the Earth.
There it is, the meter. A thing of beauty. Not so much the object, but the idea it represents. This meter bar ushered in the era of metrification. The achievement is immense. Even Napoleon, in a moment of humility, admitted that conquests come and go, but this work will endure. And he was right. This lump of metal really represents a change in our thinking. For the first time, we had measurement based on something fundamental and universal.
The concept was brilliant, but the meter's triumphant arrival was not embraced with universal enthusiasm. In fact, it took several decades before the meter was finally accepted as a standard international unit of measurement. It was on a spring day in 1875 that it all became official. The historic meter convention was signed and meter clones sent out around the world. It was the beginning of our global system of precision and accuracy. 17 countries signed the convention to form the BIPM, the Bureau International des Poids et Mesures, the custodians of international weight and measurement. It's a role they still perform today. Metrication was to be the basis for a new system of measurement, the Système International, or SI. It even led to a new science, metrology, the study and refinement of measurement. The meter had united the world, at least in theory. Alongside the meter, seismic changes had happened in how we measured time. For more than 3,000 years, the sundial was the timekeeper of choice across the world. But it was not without its problems. And the reason is, it's just not possible to fix the exact length of an hour because the shadow cast on the dial alters daily throughout the seasons. The Greek astronomer Hipparchus was the first to notice the equal length of day and night at the spring and autumn equinoxes, and that this could give us a standard for setting a fixed length of hour. But up until the 14th century, we had no practical way of doing this. It took the invention of the mechanical clock to change everything.
This is the Salisbury Cathedral clock, and it dates back to 1386, and it's believed to be the oldest surviving mechanical clock in the world. For me, this is an absolutely staggering achievement. I mean, this is the 14th century, the medieval time, and here a blacksmith and a stonemason have created something that is able to regulate time. Now, it isn't driven by a pendulum. Those sort of clocks wouldn't be invented until the 17th century. Instead, it's these weights at the back which are controlling the clock. And as the weights fall, they unwind the ropes around these barrels.
It's gravity that drives the clock. And all you need to power it is some muscle to raise the weights.
The intriguing thing is, there isn't any clock face on this clock. It was already quite an achievement in that time to get that bell to bong every hour. By the end of the 14th century, many cathedrals across Europe had built clock towers, towering up to the heavens, glorifying God, but perhaps more importantly, controlling the lives of us mere mortals down below. The clocks weren't terribly accurate. Probably the best ones lost 15 minutes a day, but they began to irrevocably change people's lives. No longer dependent on the sun, we were tied to the chimes of man-made clocks.
In the 15th and 16th centuries, as the mechanisms became more accurate, the clock face itself appeared, something we now take for granted. It then became possible to break down our day into even smaller units. For the first time, the hour could be divided into minutes and seconds. The idea came from the Greek mathematician Ptolemy, who divided a circle into 360 equal parts called degrees. He then split each degree into 60 minutes, and each minute into 60-second minutes. Which gave us the words we use today. The relationship between time and length was getting closer. We now measured the passage of time by the distance the hand travelled around the clock face. Mechanical clocks gave us a fixed hour, but actually setting them to the right time was still a problem.
We still looked to the sun and set our clocks and watches to noon when the sun was directly overhead. But that meant that each town had its own different time. For example, here in Salisbury, the clocks were over 7 minutes later than the clocks in London. The reason? Well, we're further west here, so the sun arrives overhead later.
But with the development of steam power in the early 19th century, things had to change. Because it was impossible to set busy train timetables if every town had its own different time. A single national time was urgently needed. Under the unswerving leadership of Sir George Airy, the Astronomer Royal at the Greenwich Observatory, Greenwich time became the time for Great Britain. The railways were the first to switch their entire timetable to this new time. And they did it by sending the correct time to virtually every station in the country by the new telegraph lines, which often ran alongside the railways.
Gradually, national and international time became essential for business. And in 1884, Greenwich time was universally adopted as the basis for a new system of international time zones.
The reason for its enthusiastic adoption was because the Greenwich Observatory produced the most accurate nautical almanacs used by mariners throughout the world. And as these almanacs were all set with Greenwich lying on 0 degrees of longitude, the prime meridian, at a stroke, Great Britain became the centre of the world. Time was no longer calibrated locally by when the sun was at its highest. It was set astronomically at Greenwich. But while Greenwich time had gone international, for most people, actually getting your hands on the correct time was still a challenge. And for businesses, this was fast becoming a problem.
And one family realised a cunning way to exploit this need. Every week, John Henry Belville would come up the hill here to Greenwich and set his chronometer to the correct time. And then he'd go back down to London to sell the right time to watchmakers and businesses.
By the 1940s, thanks to the radio and cheap clocks and watches, we could all run on time. Time was money. International trade, business and travel were all thriving. As the world embraced Greenwich time, our journey towards globalization started. While universal time was transforming our world, the same could not be said for the meter. 17 countries had enthusiastically signed up to the historic meter convention, but in practice, few had enforced it, and the muddle of different measurements continued, with standards and gauges differing from town to town and even factory to factory, which was to have dire consequences here in the United States. When a huge fire ripped through the American city of Baltimore in 1904, a disaster of epic proportions was unfolding. As fire crews from the nearby cities of Washington and New York rushed to the scene, all they could do was sit and watch the inferno engulf the city. None of their fire hoses would fit Baltimore's fire hydrants. Despite being less than 200 miles apart, all the fire crews were using different sized equipment. The fire raged out of control for 2 days, destroying 1,500 homes. Length measurement needed to be standardized and fast.
NIST, America's measurement body, started campaigning for better standards.
Spurred on by the NIST campaign, American industrialists soon realized that they could capitalize on improvements in accuracy. Henry Ford started commissioning increasingly accurate gauges and measures. Precise and standardized measurement meant that mass production was possible. At the same time, strict patterns of shift work tied their workforces to the clock.
It was the dawn of the modern age. For the first time, millions of identical parts could be produced at rapid speed and minimal cost. The American boom was underway.
And when you see inspectors checking parts for accuracy to dimensions measured in 10,000ths of an inch, you see where quantity production of quality products actually begins. Because parts must fit together perfectly.
It would provide a profound lesson to the world. Precise measurement had the power to change the fortunes of a nation.
But the problem with any technological breakthrough is no one quite knows where it will lead. It took the paranoia of the Cold War and the resulting arms race to trigger the next big leap in length measurement. And it led us further than we ever thought possible.
But history and our own conscience will judge us harshly if we do not now make every effort to test our hopes by action.
The stakes were rising, but our level of accuracy was failing to keep up with our aspirations. Up to the 1960s, we could measure with an accuracy of 1/10,000,000th of a meter. But an error of this magnitude in the components of a rocket navigation system would mean missing the moon by 4,000 miles. Now, the challenge was to improve the accuracy 100-fold.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
The meter bar was no longer accurate enough. A new and more precise way of measuring length was needed, and the answer lay in the fundamental properties of the universe. It was the dawn of the quantum age.
Since the 1870s, there had been a growing desire to take measurement away from earthly constants like the circumference of the globe or the length of the day,
and to tie measurement to the fundamental and unchanging laws of nature, things like the speed of light or the charge on a single electron.
It was a Scottish genius, James Clerk Maxwell, who first suggested that these universal constants could hold the key to more precise measurement.
Considered by many to be the 19th century's most influential physicist, Maxwell's theories would change the course of measurement history. He said at the time, "If then we wish to obtain standards which shall be absolutely permanent, we must seek them not in the dimensions or the motion of our planet, but in the wavelength, the period of vibration, and the absolute mass of these imperishable and unalterable and perfectly similar molecules."
Maxwell's idea was as revolutionary as the decision a century earlier to take length measurement away from the human body and base it on the Earth.
Maxwell changed the direction of the science of measurement.
Maxwell, it's hard to overestimate the influence he had on scientific thought in the 19th century. It was a very influential idea he had. And he said, well, we should be measuring length in terms of the wavelength of a color of light. But even he couldn't figure out how to really do it to the accuracy that would be required to replace the sort of old meter definition.
Maxwell was never able to turn his dream of using the wavelength of light to measure distance into reality, because the technology to achieve it simply didn't exist. But his ideas were revolutionary. It wasn't until decades later, a scientist at the BIPM, the same place where the world's master meter bar is held, would start to bring Maxwell's vision to life. Albert Michelson began to design and build machines called interferometers that would actually measure the wavelength of different light sources.
So this is one of Michelson's original interferometers. So what was he using it for, and how did he use it?
Well, he wanted to demonstrate that it would be possible to measure a wavelength of light, because light travels in waves, and then in a future time define the meter in terms of this wavelength of light.
Wavelengths of light are invisible to the human eye. Michelson's genius was realizing that when light is split and then recombined, it forms a unique pattern called interference that can be used to count wavelengths.
So by counting how many going from light to dark, take a meter, divide by the number of those, you'll get the wavelength of light, something that you can't see with your naked eye.
Right. What he had to do was build up from a wavelength of light to a meter. And in a half a millimeter, there are about more than 1,000 wavelengths of the...
Extraordinary.
It was the breakthrough that was to change the destiny of the meter.
After over half a century of laborious research, scientists were ready. Maxwell's dream was about to become a reality. On Friday, the 14th of October 1960, delegates from across the globe, from Russia and America, gathered here in the grounds of the BIPM. The fate of the meter was in the balance.
At 6 o'clock that evening, to much applause, the meter was redefined in terms of the number of wavelengths of light emitted by a special krypton lamp.
Finally, the meter bar was consigned to history. But I don't think those French revolutionaries who first came up with the idea of the meter would be too disappointed, because it was really realizing their dream of tying the meter to something unchanging and universal.
Distance could be measured accurately using a universal constant, the wavelength of light. But how could we put this new science into practice? That would need the help of a project codenamed LASER. It was the brainchild of Californian Theodore Mayman.
Well, this device happens to be the original laser.
The beauty of the laser is that it is light of a precise, fixed wavelength. By bouncing this beam off an object and precisely measuring the time it takes to bounce back, suddenly we could measure distances with incredible precision. Within years, the laser was helping us to measure our world in ways we never thought possible. And there was no better illustration of this than the Apollo 11 lunar landings.
One small step for man, one giant leap for mankind.
When Neil Armstrong and Buzz Aldrin landed on the Sea of Tranquility more than 40 years ago, on the 21st of July 1969, they left a mirror on the moon's surface. When astronomers later fired a laser pulse at it, Mayman's invention was also about to make history. The beam took just 2.5 seconds to reflect back to Earth. For the first time, scientists could calculate the distance to the Moon at any phase of its orbit to an accuracy of 3 centimeters. Lasers changed everything. They made scientists rethink what was possible. We could measure distance with extraordinary precision. Distance was tied to a universal, unchanging constant, but time was not. The second was still based on the rotation of the Earth, which is actually rather variable. Finding a better way of defining time was to come from an unexpected quarter. Just a few years before that landmark 1960 meeting in Paris, an English scientist called Louis Essen was working here at the UK's National Physical Laboratory. His passion was precision timekeeping, and he was beginning work on a new generation of clock, the atomic clock.
We've set our quartz clocks to keep time with the rotation of the Earth, but for some of our modern problems, this is not quite accurate enough, and now we're setting our quartz to keep time with the vibrations of the atom.
The theory was to define time through the vibration of individual atoms. Across the Atlantic, the Americans, at their national laboratory, were already pushing forward with a well-funded program. Back in Britain, Essen was struggling. There was little enthusiasm for his clock project, and funding was always a problem. His first experiment imploded, destroying much of his equipment. But in a classic story of the underdog winning through, Essen eventually created the world's first working atomic clock. It was called the Cesium-1, and it was accurate to 1 second in 300 years. The second was no longer based on the movement of our planet. Time was now locked to the beating heart of a cesium atom, a movement that was unchanging and fundamental across the universe. In Britain, the latest incarnation of Essen's atomic clock is the CSF-2. It's one of a global network of atomic clocks that sets our time.
To most people, this doesn't look like a clock at all, so how does it actually measure time?
Well, what we're doing here is using lasers to slow down cesium atoms. We form a cloud of very slowly moving cesium atoms, and then we use the lasers to throw that cloud upwards through an enclosure containing microwaves, and then we fall back down through it a second time under gravity. When the atoms change from one energy level to another, the emitter will absorb one very precise frequency, and we can use that frequency to keep track of time. We simply count up the oscillations.
So the number of oscillations will define the length of a second, and those oscillations are a particular property of that cesium atom. So
that's right, yes. So any cesium atom will always have the same number of oscillations per second.
The oscillations of these cesium atoms are the ticking of the clock, and they give the CSF-2 accuracy to 1 second in 138 million years. It's a degree of precision our ancestors could never have imagined. The genius of Maxwell, Michelson and Essen now touch every part of our lives. They could never have guessed their work would one day be at the centre of everything, from our banking systems to phones, GPS and the internet. These only exist because of the accuracy of atomic clocks. and their ability to synchronize time across the planet. Measurement has taken us in directions we could never have dreamt possible. But the story doesn't end there. In one last twist, scientists looked at the meter again and realized that they could now redefine length using the new accuracy of the second. It was 1983, and in a collaboration between different measurement labs across the world, atomic clocks measured the speed of light with incredible precision. The meter could finally be defined by how far light travels in a tiny fraction of a second. Time and length were intimately intertwined.
We've come a long way since the days of the pharaohs, when time was defined by the length of a shadow. After 3,000 years, time and distance are once again linked, joined together by one of the most fundamental and universal constants of nature, the speed of light. Despite all the great advances in time and length measurement, the quest is still on. Scientists are trying to create ever more accurate clocks, clocks that will only lose 1 second in the lifetime of the universe. And once they're deployed, we can only begin to imagine how it's going to change our world. Instant communication, quantum computers, planes that can land themselves. Science fiction will become a reality. And that's the beauty of measurement. Every leap in precision, from the cubit rod to the atomic clock, has led to a technological revolution.
Through history, measurement has changed every aspect of our lives. Splitting the year into seasons and lunar cycles allowed man to plan ahead for the first time and gain advantage over the rest of nature. Dividing the day still further into 24 hours was the bedrock for civilization. The fixed hour controlled the working day. And uniform national and international time allowed the globalization of industry. The world would never be the same.
The story of measurement has shaped and changed our history, and will continue to do so as we delve deeper into the atomic fabric of the universe in search of greater precision.
Next time, I meet the biggest problem in measurement: the kilogram. This 19th century artifact is the world's master kilo, and it's losing weight. Now, a head-to-head race is on to replace it. As the best minds in measurement science fight it out, there can only be one winner.
Stay with us here on BBC4, a heartbreaking tale of abuse and exploitation. Brand new Storyville, Silence in the House of God, coming up next.